Hello and welcome to this webcast on techniques for millimeter wave component characterization. My name is Suren Singh and I am a millimeter wave industry expert at Keysight Technologies. In this presentation, we'll look at why there's a need for characterization of millimeter wave components and components at millimeter wave frequencies, and what really is driving that. And then we'll look at the actual measurement of these components. Particularly, we'll look at what is required to actually make a measurement at millimeter wave frequencies. And we'll look at that from the perspective of a vector network analyzer itself, and how it is architectured. To complement this webcast, there'll be two recorded demonstrations of measurements from a millimeter wave amplifier and a millimeter wave mixer. So here's an outline of the discussion topics that we'll be using. Essentially, we look at, as I said earlier, the need for millimeter wave component characterization. Then from the perspective of what really is driving it, what are the characteristics of the components that is being looked at when you're looking at the industry. And then we'll look at a component measurement system in terms of the vector network analyzer, how it's architectured, and so on. And then once we've done that, we'll look at the calibration at millimeter wave frequencies. As you know, most of these systems aren't ideal, so calibration is a required part of the process when making these measurements. And then look at two application demonstrations, as I said, the amplifier and then the mixer, and then a summary of the presentation. In general, when you look at both the commercial industry and the aerospace industry, both of these industries rely on millimeter wave communication systems. So the key performance drivers for the millimeter wave components that are part of those systems is required that they ensure integrity of the system itself. So the actual individual components have to perform very well so that they ensure the integrity of those systems. Let me give you an example. As an example, if you look at a 5G application space, it's critically important that the components that are used in these systems, both in the transmitters and receivers, do not impact the quality of the data that's been transmitted. And so that data in particular must be, the system must be capable of transmitting a large amount of data without distortion at speeds that and required latencies less than 1 millisecond. On the other hand, if you look at the automotive and the radar EW space, there's a demand for high performing components at high temperatures and harsh environments. And so the performance of these components are pretty critical to ensure the integrity of the overall system and provide, best in class performance. Bottom line is that all of these communication systems that we're looking at, radar, and rely heavily on accuracy of the measurement system, and so the components themselves that are used in these solutions. Before we dive into the details of the architecture of a millimeter wave solution, let's first consider the types of characteristics, the key characteristics that are required of the components that are used in the building of these transceiver systems. For instance, if you look at the building blocks, there are things like couplers and filters forming the front end of the TX/RX modules. Mixers themselves, which is a big part of that, they tend to be a main component. You look at things like the fundamental conversion, the harmonics, you look at differential type mixers, a lot of integration in that area. And so you want to be able to measure that performance. Amplifiers, which impact the transmitters and sources and frequency sources and antennas as well, which are part of the building blocks of the system. So some of the key device characteristics that impact the performance are a power transfer, conversion of mixes, and the gain of power amplifiers, minimal distortion. You're looking at things like third order intercepts, IMD noise figure and harmonic products. Ensuring high quality communication systems obviously require that the measurement system itself that's measuring these components have very low uncertainties. So the understanding your uncertainties gives you a good idea of the quality of that transmission system once you put all of the components together. Some of the key measurements required of driving these for these components, clearly magnitude and phase of the characteristics, which look at things like S parameters and so on. And then the other added requirements these days is things like power measurements at millimeter wave frequencies. And in some cases, all of these tend to be integrated components, so you want to be able to do complete power sweeps, compression type measurements. So at fully corrected vector network analysis test ports. So next we'll look at the architecture of a millimeter wave measurement solution. Particularly, we look at the vector network analyzer and how this solution is all set up for network analysis. So what you're seeing here is a typical system implementation high-level block diagram. The key part of the system is obviously a vector network analyzer, which actually forms the measurement engine that does all of the computation for the different measurements, things like your S parameters, your gain compression, your noise figure, and so on. So that does all the computation. In addition, it also provides the ability to fully calibrate the measurement data that it accepts from the rest of the system. And the correction schemes can be quite complicated in the sense that these are broadband system measurements. The other part of this solution includes a millimeter wave test controller, which allows you to integrate the vector network analyzer to the frequency extenders themselves. Each of these frequency extenders, and we'll look at them in a little bit more detail later, form part, allow the users to be able to get the device close to the test port, at the same time giving you broadband capability and providing you the ability to get good signal conditioning and power to the measurement plane. Here's an implementation here. You can see the network analyzer on the top, the test set, and then the actual frequency extenders or modules as they more commonly known these days. So what are the requirements of the measurement system themselves? If you look at the system, you want to be able to bring the measurement to the device. For instance, if you look at most of the architectures for vector network analyzers, they tend to have coaxial connectors right at the instrument plane. And in the case of millimeter wave measurements, you want to be able to bring that to the device under test. As an example, if you look at this loss curve here, you'll notice that for a good 8 centimeter cable, you got about 1.2 dB of loss. So you can imagine trying to go from a test port to your device under test, and you could incur quite easily 3 to 10 dB without a problem in terms of the losses. The other thing that this poses is the actual stability of that cable. As you move it around, you will see variations in the actual performance of your measurement. So you want to be able to bring the measurement to the device. That's one requirement. The other requirement is the system architecture in terms of the stability. When you build these systems, as I showed, it is a distributed system. So the cables that go from the modules to the test set, and then from the test set back into the extender, into the vector network analyzer, those have to be stable and not impact the performance of the system as you bring it close to the device. So if you move the modules, the cables must be moving in the same way. The other thing about the stability of the system is the thermal aspects of the actual multiplication chains in the extenders. Because you're doing everything at the measurement plane or close to the device under test with a module like this, everything in that module will generate heat, especially as you're going up in frequency and you have your amplifiers and your sources and so on. And then that can introduce instabilities. And so good calibration and stability are are the other requirements of a solution like this. So that's one of the things here you can see is I'm showing a measurement after 8 hours, but over 24-hour period of a device that failed because of a system instability. So let's look at here. This you have about minus 50 dB is the spec for the device. And then you have a system that has just after 8 hours has started to drift and failing devices that would typically have not failed. So you could see that. And then in the other case, you got a system that remained stable throughout the time. And this is across frequency, and it's a measurement of an S11 input match of a device. The impact of this is very heavily seen if you're looking at these millimeter wave devices and trying to do maybe an on-wafer measurement. You got like 3,000 parts on a wafer, depending on the size, and you start a run that maybe lasts you 16 hours or 24 hours, and after 8 hours you lost about 50% of the parts because you've basically failed good parts in that case. So it's pretty critical that the device performance and it's stable, and it forms a big part of this solution. The other thing is when you're doing things like compression measurements on amplifiers, you want to ensure that you have enough power at the test port or at the measurement plane to the device on a test. And this is driven by how well the module or extender is designed and how well it can produce high power at the broadband frequencies. So that is another requirement. And then if you look at differential devices where you have two ports, like in this example here, you have two differential ports coming in. You want to make sure that you maintain phase coherence between the two ports and be able to at the same time control the phase of the stimulus. Remembering that these are distributed systems, that becomes a critical challenge as well. And then finally, if you're looking at the quality of your measurement of your components, that actually eventually drive into the quality of your communication system. For instance, if you're looking at S11 and its uncertainty of measurement has to be really small and maintained at, and maintaining that over broadband can be a big challenge. So it has to be fully corrected and a traceable measurement at the same time. So far, we talked about the need for millimeter wave component characterization. What's driving that? Clearly, a lot of the devices or the application spaces are moving in that direction. Talking about commercial applications, 5G and so on. And then you got all of the aerospace, automotive radar, which require higher frequency performing higher components. Then we looked at the architecture of a vector network analyzer in terms of the big challenges that face it. And now what I'd like to do is focus on how we actually achieve good measurement quality through calibration at millimeter wave frequencies. When you're looking at calibrating at millimeter wave frequencies, the frequency ranges are pretty wide. Look at this, it's about 500 hertz to 125 gigahertz. The challenge with that is trying to get a broad enough broadband load. Okay, you could use closed form polynomial models to describe your devices, and you could use an open short load type of technique. Problem with that, because the load's so limited, band limited, you may have to complement this with some set of offset shorts. You can use a model for the shorts, capacitive model for your open, and your load itself is a match or delay. So that constitutes what I call a closed form polynomial model. So how did we in Keysight address this challenge? Well, what we did was develop a mechanical calcit using a 1mm IEEE standard connector, characterized 4 shorts, a open and a load, providing us with full coverage across the frequency of the measurement system. It eliminated the need for a broadband load. It implements multiple shorts, as I said. And one of the other things is each of these devices are characterized. We have what we call a database model that describes them. And then when we use the model for actually extraction of the errors from the measurement system, we use a enhanced least squares fit model. And that actually is a patented technology within Keysight that allows you to actually extract quite precisely the raw performance of that network analyzer and get you the best accuracy when you're actually measuring your device, like your amplifier or a mixer, so on. So I talked a lot about quality of your system, your millimeter wave communication system, and that leads into the discussion of uncertainty. Uncertainty clearly is the only way to actually measure how well uh, your device is performing in terms of its quality and its design. So one of the things you want to make sure is your measurement system, on the other hand, has the highest level of quality in its implementation. And you could use connectors that allow you to go to frequencies well beyond 120 gigahertz, but they are not standards compliant components. What you want to do is stay within components, with standardized components like in this case, we're using a 1 millimeter connector, allows us to get standard compliant measurements, which implies ease of traceability. And also with that, you get calibration kits and devices that can then help you reduce the amount of uncertainty that you're contributing to your device, because there's specified performance characteristics around this particular connector that makes it much easier to then get good quality measurements on these systems. Power calibration itself. So receiver calibration is one of the big things. Is when you actually using a network analyzer, you want to be able to accurately calibrate the receiver broadband. And traditionally, you would use things like multiple sensors to cover the frequency range. Typically, these are waveguide sensors, and limited. The diode-based coaxial sensors are very limited in their performance and dynamic range. And so we've implemented at Keysight a broadband DC to 120 gigahertz singles, connection, 1 millimeter connection to your measurement system for power calibration. What this allows you to do is not only do traditional S parameter measurements, but then opens it up to things like gain compression, intermodulation, distortion, IMD type measurements, spectrum analysis, harmonic measurements, and so on. So you would see this in the demonstration where I show you the amplifier measurements, and having a power sensor like this forms a critical part of ensuring accuracy in your measurement and its quality. Okay, with that, having covered the calibration bit, talked a little bit about the component system itself and the different components that we're looking at. Let's look at the first demonstration of the amplifier characterization, and then we'll look at the mixer and then summary discussion. In this part of the presentation, I'd like to now show you a live demo of making a measurement of the millimeter wave amplifier. And what you're seeing on your screen here is an overview of the system. So let me show you each of the components. So the first of which is the PNAX. That's the PNA that we will be using to do all the measurements. Attached to it is a test set, and then you'll see each of these modules are connected. So we have 4 of them. However, in this particular demonstration, we will be just using ports 1 and 2 for the measurement. Here's the device under test. This is a 120 gigahertz amplifier. I have a cable that's connecting on one end and a fixed connector on the other. So that's the system. So in order to calibrate the system for power, we use a broadband power sensor, which is USB based. It goes from DC to 120 gigahertz, has a 1 millimeter connector that allows us to connect directly to the modules, the frequency extenders, and calibrate them for power. In addition to that calibration, we need to do an S parameter calibration. As you heard in the presentation, we have several shorts that provide us with the broadband calibration capability up to 120 gigahertz. We have short 1, 2, 3, and 4. an open and a load, and this is for the male or female connectors. So what I did was, in the interest of time, I went ahead and finished off all of the measurements for the setup for all the measurements. So I wouldn't be going through each measurement setup, but I will show you the different measurement types as we look at the demo. Going back a little bit, the standard measurement, notice it's fully calibrated. The way we do the calibration is using our cal-all capability. So under here, we have this cal-all capability, which allows you to select different channels. In this case, I have several channels that have been set up, and looking at port 1 and 2 and continuing and doing a full calibration. So it'll take all of the frequencies and so on. And lets you do that. So with the cal-all, you can fully calibrate each channel. So this is your fully calibrated response of this amplifier. So if you take a single sweep, and you can see now the actual gain, S21 at about 62 gigahertz, and then about 7 dB, and then it doesn't really have any gain up at 125 gigahertz. If you look at the input and output powers at that same frequency, you're looking at about 18 and 25, which is about 7 dB. Then you look at the input match, and the output match is about minus 20, and the input match is about 22 dB. So with this single setup, you can actually characterize the entire S-parameter characteristics of this device. The next thing we could do is look at a single frequency, and in this case, I'm looking at the compression at a fixed frequency of 82 gigahertz. You can see with a single sweep of that, let's take a single sweep of that and see what it comes up to be. So compression level 1 dB, compressed output power is about 4.57. Compressed power at the input is about 0.98. And at 0.98, you got about 4.5 dB out of the amplifier at that point. So this is your minus 10 to plus 4 dBm output, and you're looking at 82 gigahertz. So that's your compression. You can look at your input power here, and then you can look at your output power as well, and as well as look at the output match at the single frequency. As I said earlier, you want to be able to look at the amplifier's performance across frequency. So you could use a measurement class like the gain compression application. And here we have set up the S21, which is your linear gain, your compressed gain. We're looking at deviation from compression at 1 dB, and then your match and your input and output compressed powers. We could do a single sweep of this and look at its output. So it's about, it does a few iterations, and then it comes down to till it gets to about 1 dB compression point. Next, we're going to compute the amplifier's total harmonic distortion. And the way to do this is obviously to apply different harmonics to the device and look at the harmonic behavior and then use that to compute the total harmonic distortion. The tool I'm using in this example is our differential IQ setup. And in this case, we set a fundamental frequency of 30 gigahertz, 60, 90, 100, so up to the fourth harmonic. And then we look at the output as well at each of these frequencies. So once you've set that up and you do a measure, add your traces, so you could add each of the traces. So if I say new trace, you'll see what I've done is actually defined each of these traces to be, for instance, the second harmonic, the third, and the fourth, each of them being the second, F2, F3, and F4, each of those frequencies. F1 is the fundamental gain, and then your input power, and then your match, S22, and then you could look at S11 as well. But to compute your total harmonic distortion as a percentage of each of those parameters. So if you look at any one of these, for instance, this fourth harmonic example, you can see there I'm looking at the output of the at F4, which is the fourth harmonic output. And by doing that and taking a single measurement, you can compute the total harmonic distortion of this amplifier. So that's your input power trace. That's sitting at about minus 5 dBm. Your second harmonic, that's your gain, which sits about 10 dB. And then if you look at the gain, then you have your third and then your total harmonic distortion as well. So if you look at the total harmonic distortion expressed as 2.8%, and you can see this at 60 gigahertz and minus 50, about 120, it's about minus 30, and 90 gigahertz, it's sitting at about minus 30 dBm. So each of these are the harmonics at different frequencies. As I said earlier, another type of measurement you could do is, besides looking at its harmonic behavior in terms of total harmonic distortion for this amplifier, we can also look at its spectral response. Here we're looking at an input spectrum of 30 gigahertz. It has a harmonic at 60, which is about minus 57. We apply this to the amplifier, and here are the results of the output. You can see here at 30, 60, and 90, 0, 35, and 46. We could take a sweep of this in a single sweep, and using the network analyzer as a spectrum analyzer. In the spectrum analyzer mode, we can actually measure the spectrum of this amplifier. Just wait for that sweep to finish, and once it's done, I'll show you the actual setup. So if you look at the spectrum analyzer setup, you will see we have it sweeping from 10 to 125. The nice thing with the network analyzer is that you can actually use port 1 to apply the signal at 30 gigahertz and then measure everything in terms of the harmonics. So that is using the spectrum analysis capability. So now you're getting an appreciation for the types of measurements that a system like that integrated with broadband frequency heads can actually do. Besides actually making measurements of the different types of characteristics, you can also look at the behavior of the device in terms of its pulse profile. For instance, in this example, I'm using a pulse sweep. If you look at the sweep type, it's set up to CW, but the actual source control is set up for pulse profile. So I'm controlling the sources so that I can actually measure the profile of the pulse. In this example, you're looking at the input power here at minus 5, and you got an output power B1 of about 1 dB, so it's about 6 dB. It's about 3 dB down from the normal S parameter gain at these frequencies. Similarly, you got here about 5 dB delta between S21 and S11 in terms of the actual response. You could, let's just take a sweep, single sweep here, and now you see the response live, taking a live trace. Now this is pretty quick. In addition to looking at a pulse profile, you could look at the standard pulse behavior, look at things like its gain under pulse. Not much of a difference in terms of pulse and standard. So this is your standard measurement, if you look at it. I mean, that's your pulse measurement, sorry, and that's your standard measurement. The way to know this is if you look at the bottom here, you'll see that this is standard, and then that's with pulsed on. So let's take a sweep of this, single sweep, and look at what it updates to be. So that's your pulse response, and they're very similar. So there's not much difference in terms of its pulse behavior in this amplifier. Finally, before I go, is to look at the low frequency response. This is an example trace of a low frequency response at 900 Hertz to about 400 megahertz. We're looking at an amplifier that had about 20 dB of gain, so that's S21. And it's very simple to set up the frequencies. You basically set up your start frequency by entering that value of 900 Hertz, and it will automatically turn on the low frequency capability. So with this one setup, you could look at the low frequency capability. Hidden here is another tab, and that is the uncertainty of your measurements. Now, if you're looking at doing a characterization of a device like a millimeter wave amplifier like we have, you may want to also look at its uncertainty. What you're looking at here is a trace of the S21 in terms of having error bars on it, and looking at the upper maximum and the S21 minimum and maximum and S21 minimum in this example. And the top here, you're looking at the match, and each of these represents the amount of error. And we're going to go ahead and the new trace here. We're going to now look at the uncertainty for these measurements. Let's look under response, cal, and set up the calibration methods. I'm going to do a response cal. So that's a demonstration of the entire suite of measurements. As you can see, you could do things from determining uncertainty of your measurement up to 125 gigahertz for your S parameter of your device, like the amplifier. We can actually see what is the uncertainty. We can look at the maximum and all of that in terms of the uncertainty. We looked at LFE, the low frequency extension. I talked about standard pulse and pulse profile. Then we looked at SA, looked at using our differential IQ application for total harmonic distortion, gain compression, and then going back to your power sweep, and then your standard measurements. And with that, I conclude the actual demonstration part of being able to characterize a millimeter wave amplifier. Okay, so you've seen the amplifier characterization. Next, let's look at a mixer and how we're going to characterize that in the next demonstration. Welcome to the demo for the mixer. In this setup, we have the mixer here. That's your mixer. The input to the mixer is the port 1, which provides your RF. The LO is from port 3 that's coming in, and then your IF out of port 2. Once again, we're using a network analyzer to do all the measurements, a test set for the interconnection to the modules, as you can see. And in addition, we need to use a power sensor, and this is the Keysight USB power sensor, the 110 gigahertz power sensor. It has a 1 millimeter connector on it that will be used in the calibration for the power. In this setup, we do not use port 4, we're just using 3 of the ports. In addition to that, we have the cal kit that will be used. Again, we have all the shorts, the 4 shorts, the open and the load in this setup. So that's the hardware setup, and I'll go through next is how each of the measurements and characterization of this mixer can be done. Hello and welcome back to the demonstration for the mixer measurements. What we're looking at now is the actual instrument display, and we're going to do a few measurements on this mixer. We're going to look at its conversion, its IF response. We look at it from a CW perspective in terms of compression, and then over frequency, and look at harmonics and mixer output in terms of a spectrum analysis method. What I'd like to do is start off by presetting the instrument, so we can go through a couple of these, and then we'll recall the demo at the end of that. So let me go ahead and preset it. That should then preset the instrument, and okay, with the instrument preset, for most of the mixer measurements, what we're going to use is a measurement application called SMC. So if you look at the measurement classes on this instrument, we have all of these converter measurements. So you have a scalar mixer converter measurement. For most of the millimeter wave applications, all of the measurements are scalar. There is ability to do phase calibrations of these frequencies are challenging and at this point not available. So scalar is the measurement type we'll use. Say okay on that. So now we have a scalar setup. So let's look at the actual settings for the converter. So the mixer setup will include firstly port 1 is your input, your LO as I showed you in the setup is port 3, and port 2 will be your IF output. The mixer can be driven with about minus 10 dBm. We'll use that for this setup. Let's do some of the frequency settings. We could look at maybe 60 gigahertz to 90 gigahertz, and look at an output at maybe a fixed output of the IF at about a gig. So we're sitting at maybe a gig or 2 gigs, doesn't matter. And we can calculate the LO based on that, and you can apply that. And so now we have the frequency set up, and then the actual applied power typically it defaults to minus 15. In this case, I'll set it to about minus 25 dBm and apply that. And then the sweep type is going to be a linear frequency sweep, and apply that. So that's your setup. Now you can see your conversion. You can add new traces to this. You could look at, for instance, besides the conversion in the forward direction, you can look at the input match, the output match of that mixer. So you can apply that and say new window. We can also look at the output match in another window. You can look at the input and output power. You can apply that. And so what you got now is a full description of the mixer in terms of its conversion capability. We'll look at next is its IF bandwidth. So I'll go ahead and add another sheet with a new channel. So I'll go ahead and do that. And in this sheet, what I'm going to do is do the same thing, do a measurement setup, which includes SMC or scalar mixer cal, and say okay, apply that. So this time for the SMC setup, we want to look at the wider bandwidth. So we look at the IF response. So what I want to do is maybe look at 10 megs to about 5 gigs. I'm going to look at a fixed CW frequency, maybe at input of 77 gigahertz. So front end radar receiver maybe, and then calculate my LO. So now I've got an LO that's set up for me automatically. Apply that. So now I can look at the IF response. The actual power, we're going to apply about minus 20 dB for the RF input to this, and we'll apply that. And now we have it all set up. Again, still doing a linear frequency sweep, and the mixer setup is still the same, except we will set up the port 3 is being used to apply that. And now you can see your conversion again, but this time you could look at its response in terms of the IF as well. So let's add a few new traces. Firstly, we're going to look at the I power, that's the input power, and look at the output power. Again, apply that. We looked at the conversion. We can do the match. And the output match as well. So you have all of that. So what you're seeing here is the actual output power. You can see it's starts around minus 10 and then drops down quite a bit. So this is across the 10 megs to 5 gig output. So you can see the bandwidth response of the IF. On this trace here, you're looking at the input power, and then you can look at the conversion as a result of all of that. So that's looking at the actual conversion bandwidth of the mixer. Next, we look at starting to look at compression characteristics of this mixer. Let's start with a CW compression measurement next. And what I'd like to do at this point is go ahead and load the pre-demo state. So go ahead and recall that demo state. Now here we have the IF response we just did. So for the CW compression, we could go again, still use the SMC application. In this case, we're looking at things in terms of just power sweeping. And you look here, we're looking at -40 to about 5 dBm. Mixer frequency is set at 77 gigahertz with the 1 gig IF. Mixer power for the LO is fixed at -10. And your setup is still the same. So what you're seeing here now is a measurement of the actual compression, and we can take a sweep of that and look at what it looks like. So it's pretty quick, but like a continuous, you could start to see around 1 dB compression point. So you could use the markers like we did in the like you do with the amplifier. You could do a marker search and then look for compression and compression search, and that's what you're looking at, the 1 dB compression point at a fixed 77 gigahertz bandwidth with 1 gig bandwidth. So that's a single frequency. If you wanted to look at a wider frequency, you can use the gain compression measurement application, which allows you to look at the mixer gain compression. In this case, we're actually going to look at a 77 to 86 input RF input with a fixed IF of 1 gigahertz. You'll notice we're doing a frequency linear sweep. We are looking for a 1 dB compression point in this setup. Yet power will be swept from -30 to about 6 dBm. So that allows us to get it into compression. And then under the compression characteristics, the tolerance, the maximum number of iterations to get to the compression point is fixed. The mixer frequency is again setting up the mixer power at -10 and its physical setup as well. So let's do a quick measurement. And you'll notice it starts to do iterations at the bottom, and as it goes through the iterations, it's trying to achieve a 1 dB compression. So you look at the measurement output, you have a change in the gain for this particular setup about 1 dB. So that's the compression output that we want. So this is the compression power at the output, and that's the change in gain. And then again, the compression power, the input, your conversion, and the gain as well. And then the match at compression for this. So there's several measurements that can be applied to this setup, and they listed here. And you can see delta gain, compression of gain at the gain at compression, and the deviation from compression, and so on. So that should that's your compression point part of it on that mixer. So we've done a mixer conversion, IF response, CW compression, and gain compression. Next we'll look at mixer harmonics. To do the mixer harmonics, what we will do is use a tool called Differential IQ. What this tool allows me to do, if you look at the setup, is allows me to set up different frequencies. For instance, I've set up the input frequency 71 to 76. I've set several IF frequencies. So each of these frequencies represents 1, 2, 3 gigs IF outputs, and then I've also set up the LOs at an offset for each of those frequencies. I will be utilizing these frequencies as measurements at the output. So you would notice that always on is port 3, which is your LO, set at -10, and then your port 1, which is going to choose frequency 1 to start with, and we can choose any other frequency we want, but will be set to -20 dBm, and port 2 will be doing all our measurements in this application setup. So with that setup, let's go ahead and look at some of the measurements you can do. For instance, in the first screen here, you'll see that we can actually do a measurement of the input power, the output power, and the conversion. A standard S parameter measurement, which is you can define these traces quite easily. If you look at the screen, what I got there is input power, and if you look at it, it's defined as A1, which is your R1 input to the mixer, the output power being B2, which is your port 2 receiver, and measuring the frequency at 1 gigahertz, and then your conversion or your gain is B2 over A1 at the fundamental frequency and at the conversion frequency. So B2 is measured the conversion frequency, and that's at your input frequency relative. So that's your conversion. So you could add other parameters here, and you'll see I've added things like RF, LO, RF leakage. We're looking at the LO frequency on port 1, ratioed to F5, and then B2 at F5 as well, LO to IF leakage. So LO to RF, LO to IF. So looking at what the LO signal of F5 looks like on port 1, which is the input to the mixer, and this one is looking at the LO frequency coming out, anything coming out with the IF. So we look at each of these a little bit more in detail as we look at the different screens I've set up here. So this is your LO RF leakage and your LO to IF leakage. So LO to RF is about -62 to -88. So it looks reasonable for this mixer. Next, we look at another characteristic of the LO, and in terms of its actual leakage itself. So we look at the LO power at its fundamental, then at the second and third. So you'll start to see the LO power drop quite a bit. So how do we define those traces? If you go into new trace, LO power at second and LO power third is your port 3, but all the time using port 3, but you're measuring the frequency F6, 7, which are the LO frequencies that are offset by about a gig. So that gives you the LO leakage through into the mixer. So this gives you a better understanding of the mixer behavior. The other one to look at is the RF, and looking at the first IF, the second IF, and the third IF frequencies. So 1, 2, and 3 gigahertz. Again, you can see the measurement. So we could take a trace, we could take a measurement of this. Let's go ahead and do that and get some results and look at the data. So as expected, you know, your LO leakages are pretty low down here, and your third thermonic of your IF is pretty low, -58 at the operation of that mixer. So that gives you a full understanding of the harmonics, and with this tool allows you to actually fully characterize it using the differential IQ setup. The next thing we look at is some of the mixer performance using a spectrum analyzer. This is using the measurement application called spectrum analysis, and in this measurement application, basically you could set up the spectrum analyzer such that you control each of the sources. So if you look at here, you have port 3, it's set on, it is CW75. Port 1 is set on at a frequency of 76, so that gives you a delta of basically 1 gigahertz. So we're going to look at the 1 gigahertz delta. We got this port at the LO frequency -10 and -20 dB. So the spectrum analyzer is going to sweep pretty much from 500 megs to about 5 gigs again, and look at all the harmonics that appear across that band. So with that, take a sweep of this and we look at what it looks like. So single sweep, and it should update. And what you're seeing here, the first one obviously is your 1 gig. That's at -10, which is about the conversion of this mixer, of this particular mixer. And then you port 2, your second, your third, and your fourth is about -100 dB down. So it's pretty low, the second and third and harmonics of this mixer. So with this, with the setup that I just showed you, you could do your conversion, your mixer, your IF response, your CW compression, and fully characterize your mixer for all of these characteristics. If you're using this as a front end to either a receiver for an automotive radar application, 5G, or any of the AD applications, this particular measurement setup suite allows you to fully characterize at millimeter wave frequencies a mixer. And hopefully you found that both the demonstrations that you've seen useful. Clearly, from a summary standpoint, there's a clear need for utilization of millimeter wave frequencies for more information at the higher, as we demand more of systems. So that requires, network analyzers that can actually do these measurements, and a distributed architecture like you see here is key to supporting characterization of those components. The other thing is to be able to fully calibrate it both for magnitude and power is a key part of that. And as you saw in both the demonstrations that we looked at, the software application is a key component to making that possible as well. Finally, I would like to say thank you for your attention and trust that you enjoyed this.